Give me 1 second. The audio is connected. 1 second.
This USB you can connect directly to this. This works better. Just directly connect.
No, it's not the correct audio now.
How about now? All good? Okay. What is this? Is it good? Can you hear me? Okay. Okay. You heard the bell. Let's get started. People are still coming in. It's good that there are many people who are here. Looks like there's an event going on, so maybe it was difficult to enter. Okay, today we're going to continue with combinational logic first, and then we're going to jump into sequential logic. So we're actually going to be able to build circuits that are meaningful based on the components that we have started with. And there is nothing magic over here. Remember, we start with the transistor and we built logic gates. We're going to build more logic gates, and everything is logical. Okay, I don't know why this is not working. Okay, yeah, as I said, first we will complete combinational logic. If you remember, we covered a bunch of combinational logic blocks starting from basic logic gates. We did decoder, multiplexer. We're going to use them again today to build memories. We built a full adder. I'm going to show you again. And we stopped at programmable logic array. And last time we covered standard form representations, sum of products and products of sums. And also we did logic simplification. We have Boolean algebra, which you had known hopefully before, right? A little bit at least, with maybe different notation, but it's the same in the end. It's all logic, Boolean logic. So we also discussed that a programmable logic array enables sum of products representation and enables building any circuit. And this is what we did last time. This was one of the, maybe it was the last slide actually. We were implementing a full adder using a PLA. And programmable logic array essentially has all input combinations. This is actually a decoder, if you remember. It's a 3-input decoder over here, ABC. And all input combinations, whenever one input combination is enabled, only one of them is raised. So if A is 0, B is 0, C is 0, this is 1 and everything else is 0. That's the operation of a decoder, if you remember last time, right? So programmable logic array in itself uses a decoder, and you can actually connect the outputs coming out of these gates to the inputs of these OR gates. And this is really the sum of products representation, right? And this was the connection that we built to realize the truth table of full adder using a programmable logic array. I didn't tell you exactly how you would program the connections, and you don't need to know that, except for connecting these inputs to these outputs of the AND gates to the inputs of the OR gates over here. But there may be many ways of doing that. That's beyond the topic of this course. But essentially, a programmable logic array enables a sum of products representation in a programmable way. So it can and enough outputs in your programmable logic array. Okay, makes sense, right? Now I'm going to introduce logical completeness, which you may have seen also. This is a very basic concept, but any logic function we wish to implement could be accomplished with a PLA. Now, this is not magic because you knew this before. Programmable logic array implements a sum of products form, and we said sum of products form is a canonical representation of any truth table. Any truth table is any logic function in the end. So I just proving you what I just said over here, right? Basically, another way of looking at it is this: PLA consists of only AND gates, OR gates, and inverters. Meaning, if you have AND gates, OR gates, and inverters, you can build any logic function. But you knew that before also, because that's again the sum of products representation. You just need to program the connections based on the sum of products of the intended logic function. So basically, we call the set of gates AND, OR, and NOT logically complete because we can build any circuit to carry out the specification of any truth table we wish without using any other type of gate. Now, this is nice, right? But it's also true that NAND is logically complete by itself. So if you just have a NAND gate, you can build anything because you can actually represent AND or NOT using NAND. So is NOR by itself. I'm not going to prove this, but it's fun for you to try it out. Okay? So that's logical completeness. Another way of looking at it is sum of products form. Okay, now let's look at some more combinational blocks that might be useful in the later lectures, plus in your labs. I will not go through everything combinational because that would take a really long time, many lectures. We're not going to go over, for example, multipliers, etc. Your book has some combinational blocks, and I would recommend, if you're interested in looking at combinational blocks, reading the chapters that I recommended earlier. And these are some of the examples. Okay, so comparator. Comparator sounds good, right? Or let's start with an equality checker. You can build the comparator yourself. So equality checker is a comparator. It's comparing two values, and you compare if they're equal. So the idea is to check if two n input values are exactly the same, bitwise. For two 4-bit values to be exactly the same, each of the bits at the right position should be equal to each other, right? So we're going to build a 4-bit comparator, and it's not going to be, the higher level modular picture will look like this. Basically, we're looking at two inputs, A and B. Each of them is 4 bits. That's the notation we will use. And basically, this is checking whether they're equal. If A and B are bitwise equal to each other, if every bit in the right position is equal, then you'll get a 1 at the end. Otherwise, you'll get a 0. And this is how you would build that circuit with XNOR gates. And again, you can convince yourself. So each bit you check is A3 equal to B3. This XNOR gate evaluates to 1 if A3 and B3 are both 0 or both 1. Okay? Otherwise, it evaluates to 0. And if any of these evaluates to 0, meaning if any of the bits is not equal, bits are not equal between the two inputs, then you'll get a 0 at the end. For this AND gate at the end to evaluate to 1, all of these XNOR gates should evaluate to 1. That's the function AND, 4-input AND. And for all of them to evaluate to 1, each of the bits that are input to the XNOR gate should be equal. Makes sense, right? That's the XNOR function. Again, you can convince yourself if you forgot what is XOR, what is XNOR, you can look at the truth tables. There's no magic over here. Okay, so that's our equality checker. Sounds good? Okay, so if you want to build other stuff like to check whether something is greater than or less than, whether A is greater than B or less than B, then you need to build a subtractor, which I'm not going to build, but I'm going to show you a picture where a subtractor exists in this thing that I'm going to call the arithmetic logic unit. Has anybody heard of arithmetic logic unit before? ALU? Okay, that's good. If you haven't heard, don't worry, you're going to learn about it. This is essentially the unit that does both arithmetic and logic, as you can see based on the name. It exists in all processors, and this is really the core execution unit, if you will, that we will see more on later. But basically, the basic idea is to combine a variety of arithmetic and logic operations into a single unit, a module. But this unit will perform only one function at a time. That's the idea. And one function will be dictated by what we will later call an opcode, but I'm going to call it a function today. But you will see when we talk about ISA later on, we'll tie it to the higher level software structure as well. But usually it's denoted with this sort of symbol. You usually see ALU. Sometimes you don't see ALU, and it kind of looks like this. And this symbol is arithmetic logic unit. It takes two inputs, A and B. Each of them are n bits wide, and then has an output n bit wide. There may be other outputs also, but in this case, we see only one. And there's, as you can see, a function input, F input over here, that's 3 bits. So this arithmetic logic unit is capable of distinguishing between 2 to the 3 functions, 8 different functions. And to be able to distinguish between those functions, you need kind of a decoder, right? F specifies your function in 3 bits, and you need to decode which function you're actually going to execute by having a decoder internal. And you will see that soon. But assuming that this is the specification of the function, someone needs to specify this, of course. Later, we will see how we will specify this based on the specification of the instruction set architecture at the higher level. We're not dealing with that yet. We're going to build up to that. For example, if an encoding of 000 specifies that this arithmetic logic unit should output y equals A and B. So that's a logical operation, as you can see, bitwise AND. This is A or B, this is A plus B. In this case, it's actually a plus, addition. It's an addition operation, so don't get confused. This is not used for future use, let's say. And there are other interesting cases over here, A and not B, A or not B, A minus B, set less than, etc. We're not going to talk about everything, but your book covers it. And this is the complete logical specification of that unit over here, as you can see. So in this case, function is implemented in a different way than I imagined, but it's fine. You can imagine different ways of building it, but this is one way of building the arithmetic logic unit. If I actually specify this, you could have built in a different way. So let's take a look at one example. I'm not going to go through everything over here clearly, but you can read it. There's no magic over here. For example, let's take a look at let's take an interesting case. Let's assume that the function is 0, 1, 0. Bits 2 to 0 is 0, 1, 0. What happens in this? So here's a multiplexer over here. This multiplexer outputs y. That's the output. Let's go backwards, if you will. Our bits F1, 0 in this particular case is 1, 0. 1, 0 is 2. So the result should come from here. Right? So we're going to take this and pass it to the output based on the specification of the last 2 bits of F. So what is this? This comes from the adder, as you can see. This is an adder. And this adder takes A on one side, unconditionally, does not depend on the function. And it takes something from here, conditionally, based on this F. And you can see that it's another multiplexer. If F2 is equal to 0, which is what I specified that we wanted to examine, then it takes B. So this passes B. This passes A, you get A plus B at the end, and A plus B propagates to Y if F2 is 0, F1 is 1, and F0 is 0. Makes sense, right? So that's how you get A plus B. Now, let's take a look at A minus B very quickly. A minus B differs only in F2, right? This is 0, 1, 0, this is 1, 1, 0. So we still take this, this output of this adder, but F2 is, in this case, 1, which means that we take the complemented thing over here, okay? So this is actually a 2's complement, basically complemented. Basically, you do a 2's complement of B, which means that you get minus B, and you add A to minus B over here. Make sense? Okay, you can read more about that later on. Okay, so I don't want to go over all of this, but you can see some other ones over here. Okay, so again, I showed you kind of the subtractor using 2's complement representation. You can read more about that, but there are other combinational logic structures like shifting, rotating, which you will do in your labs. Maybe not everything, not rotating maybe, but shifting, multiplication, division. So all of these are built using logic gates and modules that we have seen. Okay, no magic, right? And if there's a mistake, you can find it. You can actually build better structures also, and this is one way of building the ALU. So ALU, of course, depends. The functionality of the ALU depends on what you add to it. In this case, you have 8 functions. One of them is not used, but you may have 32 functions. You may have actually 64 functions. So it could be something very capable or something not as capable. And you clearly run into trade-offs in terms of capability, functionality, as well as area overhead and the latency, etc. Make sense? Okay, good. Okay, so if you want to learn more, there's more. I'm going to show you a couple more things that will be useful later. One is tri-state buffer. This is an interesting thing because it's nice to, it enables really gating of different signals into a wire. I actually told you that very briefly in an earlier lecture. It looks like this. It's one of the simplest structures. Basically, if you look at the truth table, if enable input is 0, the output is floating. Basically, whatever it's connected to, A is not connected to Y if enable input is 0. If enable input is 1, A gets connected to Y. Basically, Y gets the value of A. Makes sense, right? So floating signal is a signal that's not driven by any circuit. We have seen it before, remember? If we don't connect any of the top part, PMOS part, as well as the NMOS part of a CMOS gate to the output, you get a floating signal on the output. We said that it's not that bad, and that's how I foreshadowed the tri-state buffer. Now we're going to see how tri-state buffer works and why it's useful. So a floating signal means that it's not driven by this circuit, but there could be another circuit that's driving this wire, Y that's connected to. So now you can connect multiple tri-state buffers to a single output and decide which one to enable, which one to disable. So where this is useful, we will see. Okay, floating signal, we discussed this already. It's open circuit floating wire. So a tri-state buffer, if you think about it, acts like a switch, right? If enable is 0, the switch is open, A is not connected to Y. If enable is 1, the switch is closed, A is connected to Y. Sounds good, right? Okay. So why is it useful? Now let's imagine a wire connecting to a CPU and memory. These are big blocks that we're going to think about. At any time, only the CPU or memory can place a value on the wire, but not both. If they both place a value, then there's some collision on the wire. You'll get short circuit. You can have two tri-state buffers, one driven by the CPU and another driven by the memory. And they're both connected to the same wire, let's call it a bus. And you ensure with your control logic that at most one is enabled at any time. So this is one example. Later, we will see this as part of a larger processor. But right now, we're building up. So this is CPU, this is memory, and I'm going to call this a shared bus. Bus is essentially a collection of wires. And this exists in real processors. In real processors, like this system, that system over here, this system over here, there's a system bus where different components get connected to and they communicate with each other through this bus. So in this particular case, CPU is connected potentially to the shared bus. Memory can also be connected, but by designing the control logic such that at any given time, only at most one of these control signals are enabled, or one, you ensure that either the CPU puts a value onto the bus or memory puts a value onto the bus, but not both at the same time, right? So why is this useful? CPU can put some value and then send the value to memory. Now your book has the bigger picture, which basically, for example, in this case, the processor, if it wants to put a value on the bus, the control logic sets the enable to 1. No other control logic should set these other enables to 1. Only the processor now gets connected to the shared bus, and the value gets loaded or gated onto the bus, and this value propagates based on physics principles. And assuming the processor, let's say, wants to, for example, write this value to an Ethernet controller to go out of the network, this value goes through this buffer. This is just a buffer, as you can see. It's not a tri-state buffer, but it could also be a tri-state buffer. In this case, it's a buffer, and this Ethernet can take that value and do whatever it needs to do with it. Make sense? So now we're really connecting different components. These are high-level components that we have not designed, but they operate based on all logical principles that we have been using. But the basic value of the tri-state buffer is enable communication. It's one method, one logical structure that enables communication by enabling different components to place some logical value on a wire. Make sense? All good? Okay. This may be simple, but it's good to think about that. So tri-state buffer is interesting because it's a switch. You can play tricks with it. I'll go through this relatively quickly, but this is a multiplexer. It's a tri-state buffer implementation. of a multiplexer. It's a 2-to-1 multiplexer. You can see that if S is 0, Y is equal to D0. If S is 1, Y is equal to D1. Basically, you select between D0 or D1 based on the value of S. Makes sense, right? And this is your book's notation. It's not the best notation, but S, the inverted value of S is the enable input to this tri-state buffer, and the regular, not inverted value of S is the input, enable input to this tri-state buffer. Yes?
Before the in from bus buffers, we kind of have to communicate between the buffers or between something to enable the correct from bus buffers, and for that we need another kind of shared bus system.
I mean, yeah, what I said over here in this case, your book just shows buffers. This basically is okay, right? Somebody puts a value onto the shared bus, and everybody sees it. In this case, right? But if you don't want everybody to see it, then you need another. You need to make those tri-state buffers. Make sense? Okay. So in this case, your book decided, for simplicity or whatever reason, that these are buffers and not tri-state buffers. They don't have enable inputs. That's the only difference. But yes, if you want if you want a communication to happen between just the processor to memory, for example, there needs to be a system that enables the processor to gate the value, and another system to enable only the memory to receive the value. But then you need tri-state buffers. Okay. So that's a multiplexer using tri-state buffers. You can take it to the next level. This is a 4-to-1 multiplexer using tri-state buffers. And again, enable inputs are controlled based on 2 bit values, S1 and S0, select values, if you remember from the multiplexer. We're going to build these multiplexers more and more, so that's why I'm kind of exercising you over here. If S1 and S0 are both 0, D0 gets connected to Y, as you can see, right? And then you can play the logic game and figure out all of these. Okay, so it's beautiful, I think. Recall this was the 4-to-1 multiplexer that we built using and then NOT gates and OR gates before. So it's also interesting to see that multiplexer, part of the multiplexer is a decoder, right? I didn't say that last time exactly, but if you look at this part, that's the decoder. Okay? So multiplexer and decoders are kind of like sisters. Okay, yes?
Using the floating value, could I build like a multiplexer that is like, for example, for each one, that takes is one output depending on let's 0, 1 or floating?
I mean, logically, yes, right? Logically, you can do anything, except as you put more and more things that are connected to a bus, lower level abstraction kind of breaks at some point because you're loading the bus too much potentially, and the capacitance on the bus is increasing. And as a result, you may not be able to operate things very well. So this is the logical abstraction. But if you take the logical abstraction too much without knowing what's going on underneath, sometimes you may break things. Okay, so it's always good to know what's going underneath a little bit. Okay, so let's dig a little bit deeper, a little bit more underneath. How would you actually implement this tri-state buffer using transistors? This is one implementation over here. Again, I will not go through this in detail. You can because I don't want to go into that lower level abstraction more than needed. But this is again not magic. This tri-state buffer is not magic. You can see that this was an inverter we had. Instead of having an inverter, we actually have an enable signal connected to the output. And enable bar is controlling the top one, and enable is controlling the bottom one. So if you can convince yourself that if the enable signal is set to 0, both of these transistors are off. So neither the high voltage nor the low voltage is connected to the output. If enable signal is set to 1, both of these transistors are on, and this looks like an inverter. So this is an inverting tri-state buffer. And then you can add another inverter to actually get a non-inverting tri-state buffer. So there's no magic, as you can see. Okay, so now we've covered essentially everything that I wanted to cover. Clearly there's more, but we don't have time for it. Let me quickly talk about Boolean algebra simplification a little bit more, because I want to introduce some things that we're going to use later on. Clearly we have done this, and you should be able to simplify this full adder in SOP form This is kind of like the PLA type of form, but you can also build this without a PLA, as you can see. This is our full adder. If you want to simplify this full adder, you can use Boolean algebra, you can use different methods, etc. But I'm going to show you other ways of simplifying things as well. So this is the simplified full adder. These equations are actually good to know. So the sum bit is an XOR of A, B, C in, and carry out bit is a 3-input majority function of A, B, C. And these are the simplified versions. Okay? Of course, you can express XOR with AND and not or just NOR gates, but I'm not going to do that over here. Okay, so automating simplification actually is important. I'll just give you the key idea of how electronic design automation tools operate. They really operate based on these equations. And what they essentially, they try to reduce the number of gates or inputs and reduce implementation costs so that you can get better latency and power. And each gate has some sort of characteristics, assuming it's implemented in some sort of underlying technology, right? So for example, 3 nanometer CMOS technology developed by TSMC, and in this particular library that's optimized for low power, AND gate has some latency characteristic, and it has some power characteristic, not just AND gate, it has to be some input AND gate, 2 input AND gate has this characteristic, has an area characteristic. So for every single gate, you may have these characteristics. And the goal of the design automation tool, and if you don't have that design automation tool, the goal of the human who's actually doing that mapping is to figure out a mapping from a high-level Boolean equation to a really nice implementation that satisfies some goal. The goal may be lowest power, highest performance, lowest latency, lowest area, a combination of all of those. You can see that the design space can be huge, right? So in general, minimizing logic is good. But mapping the minimized logic to the underlying gates, sometimes you may not want the completely minimal one, but a little bit less minimal logic that maps to better gates, right? It's good to think about that. Okay, but automated design tools do all of that today to some level of goodness, and they're much better than in the past. But almost always they use theorems and Boolean algebra. For example, one key tool is really uniting theorem. There needs to be systematic techniques that these tools behave. So uniting theorem is important. It basically simplifies this function, right? If you look at this function, B's value changes within the rows where F is equal to 1, right? This is called the onset. Essentially, F is equal to 1. This is when the function is on, which means that you can eliminate B, right? A's value does not change within the onset rows. If an input can change without changing the output, that input value is not needed. So B is eliminated, A remains. Because if you look at this, this says F's value doesn't depend on B, right? Makes sense, right? Whether F is 0 or 1, which are the only 2 possible values in our algebra, the output is always 1. So I don't care about B. That sounds good. Similarly, so you could also have figured this out, of course, but this is a simple equation. You could imagine a truth table with, I don't know, 30 inputs and, I don't know, 20 outputs. Now you can actually play these tricks by figuring out where things change or don't change based on the onset, okay? And you can actually develop a program that figures that out. That program may operate on graphs and different things, which we're not going to go into, which is also a fascinating topic, but that's not the subject of this course. The subject of this course will show that this is possible to do and hopefully give you an intuition that it is possible to do. Again, the same thing over here. G's value, G's onset is here, and it's not dependent on B. So in this case, you can again, it's not dependent on A in this case. So regardless of whether or not A is 0 or 1, G is 1. So G is really B prime in this case. Okay, so these are the techniques. Essentially, the essence of simplification to put in words, you find 2 element subsets of the onset where only one variable changes its value. The single varying variable can be eliminated, okay? And you can do that for a larger number of variables also, a large number of elements. Now let me introduce one more thing, priority circuit. So we're going to assume that we have some requesters. These could be implementing what I showed you earlier. There could be some requesters that are requesting a wire, for example, so that you can enable an input to be gated onto the wire. We have some priority levels. And then outputs are grant signal for each requester. So let's take a look at a 4-bit priority circuit. Imagine a bus requested by 4 processors, or the earlier picture where you had 4 things that could potentially be connected to the bus. We're going to assign a priority level to all of them. And these could be the enable signals that go into the tri-state buffers. The outputs are Ys, inputs are As, and A3, A2, A1, and A0 are different processors in this case. And the priority level in this case is static, meaning if A3 requests the bus, it should get it. It has the highest priority. So if you think about it, these are the request signals from A3, A2, A1, A0. And these are the who got the bus signal. If Y3 is 1, A3 is granted the bus. If Y2 is 1, A2 is granted the bus. If Y1 is 1, A1 is granted the bus. If Y0 is 1, A0 is granted the bus. Of course, for this to work, no two, let's say, requesters should be granted the bus at the same time. Okay? And we're going to build the truth table. And the truth table looks like this, basically. If A3 is 1, set to 1, the output Y3 is 1, and everything else is 0. Now you can simplify this, right? Y3 is essentially A3. Okay. If A3 is 0 and A2 is 1, Y2 should be 1, and everything, all of the other outputs should be 0. Again, priority. A2 has priority over A1 and A0, but not A3. If A3 and A2 are not requesting, but A1 is requesting, Y1 should be 1, and everything else should be 0. And if only A0 is requesting, Y0 should be 1, and everything else should be 0. And if no one is requesting, all of the outputs should be 0. Right? Now, what I built over here is a priority circuit that kind of controls these enable bits. Okay, just to connect the dots over here. Maybe I should have copied that slide over here because it's a bit far. Yeah, this thing over here. So these enable signals can be dictated based on the request signals coming from processor, video, Ethernet, and memory. And enable signals are Y3, Y2, Y1, Y0. Or, yeah. And the request signals are A3, A2, A1, A0. Now, this is how you can connect things. You can have a priority circuit. Does that make sense? Okay. Now, let's simplify this priority circuit. This was our truth table. I'm going to introduce something to the truth table that's called an X. This is an important thing that's going to make your life easier in the future. X means don't care, basically. It means I don't care what the value of this input is. I'm going to collapse this truth table into this truth table with X's. So if A3 is 1, I don't care what A2, A1, A0 are. Y3 is 1, and Y2, Y1, Y0 should be 0. Same as here. If A3 and A2 are 0 and 1 respectively, I don't care what A1 and A0 are. This should be my output over here. Okay, so now you understand that, right? Now you collapse the truth table. This makes our life easier because we can express the equations much more nicely. So for example, here, Y3 is equal to A3 because I don't care about anything else over here, any other input, I should say. Y2 is equal to A3 bar A2, which is over here, and I don't care about the other ones. They could be anything. This is essentially the uniting theorem in action. I showed you the uniting theorem with 2 variables, but we've collapsed them into don't cares over here. In the uniting theorem, we could have made that don't care also, right? I don't care what B is. The output of the function is really dependent only on these inputs. Okay? And this is the realization of our priority circuit, which is actually simpler and easier to read than the truth table, as you can see. Okay. Okay. What I'm not going to cover is Karnaugh maps, which is really fun, but we don't have time for Karnaugh maps, and it's not really used in general. But you can imagine a pictorial representation of minimizing circuits. Actually, this could get very complicated. I shouldn't say very simple. If you have more than 5 inputs, it's very difficult to visualize things. That's the reason why it's not used in general. But you could have a pictorial way of minimizing circuits by visualizing opportunities for simplification. We saw that kind of in the uniting theorem. If B's value doesn't change, when A's value changes with different combinations, you can eliminate B. You just need to visualize it. We kind of visualize it, but I'm not going to go to it. So this is to study on your own. I'm not going to ask you anything about that in the exam, etc. but you may want to have some fun. Sounds good? Okay. Okay, now we're done with combination logic. Any questions on combination logic? Yes? Say it again?
If I question an exam of logical simplification, which shows up, can I answer it using Karnaugh?
I mean, you could, yes. Yeah, you could use any technique to answer the question, no problem. As long as you get to the right answer. Okay. Now we're going to start sequential logic, which is going to add a real flavor to our circuits. Because so far we have a disadvantage. We cannot remember anything we have done, right? And as humans, if you cannot remember anything you have done, you're not fully functioning. Okay, so let's see. Today I don't think finish is going to be realistic. We're not going to be able to finish sequential logic today, but we're going to continue tomorrow. And we're going to move to a hardware description language and Verilog and timing and verification. And we're going to discuss labs also a little bit tomorrow. Okay, so this is what we're going to see. We're going to see circuits that can store information. I'm going to build up to a lot of these. Well, in some order, not the same order. And we're going to look at concepts, important concepts like state and clock. And I'm going to also introduce asynchronous versus synchronous. That's going to be, even though we're going to assume synchronous circuits in all of these, in all of this class, it's important for people to know asynchronous as well, because it's a good contrast to the clock concept. And we're going to talk about finite state machines. So these are some readings. Basically, just to show you that how important memory is. We're going to see importance of the memory a lot going into the future, but no real computer can work without memory. Most of a computer is actually memory, if you think about it. And we're going to start building these memories in this lecture. In fact, memories are more, even if you look at a processor chip, most of it is really sequential. So this is the importance of sequential logic, I would say. These green parts, for example, are all sequential logic. And I didn't mark everything sequential over here. And people are adding more and more 3D stacking technologies where you have more and more sequential logic, more and more memories. I could keep going through this. This thing, for example, most of it is really memory. Most of it is sequential. Okay, so what does the sequential mean? So we've seen combination logic. The circuit output depends only on the current inputs, right? That's combinational. But we want circuits that produce output depending on both current inputs as well as what we have done in the past input values. These are circuits with memory, essentially. You can also think of this as storage element. There needs to be some storage element, basically, to store the past results, if you will. The question is, how can we design a circuit that can store this information? We're going to start with very basics. We're going to call this entire thing a sequential circuit. So a sequential circuit is not just a storage element, but also the combinational circuit that goes along with it. And the whole purpose of this is to solve a problem at some point, right? That's why map the inputs to the outputs. So we need to talk about capturing data. And this may be a little bit surprising if you haven't done your readings. If you have done your readings, I'll show you something slightly different. And there are parts in Harris and Harris that I don't quite agree with when in their RNS latch. So you should take a look at my explanation, also Harris and Harris's explanation. But we're going to start with something basic, cross-coupled inverters. Looks like this. This is combinational logic. Or is it combinational logic? It's built using combinational elements that we have seen. But what I have done here, and what people do here is, you have inverter, you have another inverter, and we have cross-coupled them, meaning we took the output of this inverter, called it Q, and connected to the input of this inverter. And we took the output of this inverter, called it Q bar, and connected to the input of this inverter. Sounds good, right? Now, this has two stable states. If Q is 1, Q bar is 0. And if Q is 0, Q bar is 1, right? That sounds good. And that's logical. So these are the stable states. And again, you can read your books. Books are fine in all of these. It also has the third possible metastable state with both outputs oscillating between 0 and 1. We'll see this later. Again, this is below our digital abstraction. But if for some reason, somehow, the outputs are not fully 0 or fully 1 at the analog level, lower level, voltages are lower, you actually go into an oscillating state. You keep oscillating between 0 and 1, 0 and 1, 0 and 1. At some point, you settle. This is metastability. You don't need to know about that really for the purpose of this course, but it's important to know because we're going to build some more complexity into our circuits to avoid that. Okay? So this is one problem that the circuit has. Sounds good, right? Is there any other problem this circuit has? Well, I guess I kind of gave away. This can capture data, right? We have captured a value of 1 in Q or a value of 0 in Q, and that keeps going, right? It never ends. It has, as long as this is powered on, Q is 1 or 0, unless you go into the metastable state we're going to ignore for now. Okay? So we've captured value. Using combinational logic structures, we actually built a sequential storage element. Now, the problem I see here is, how do I set Q? There's no way I can actually change Q, right? Unless I go physically do something to the wire. There's no input over here. Basically, it's not useful. Even though it is the most basic sequential storage element, it's not useful because we don't have a control mechanism for setting Q. Now, we're going to build that control mechanism. It will also have a metastable state, and we're going to try to avoid that, and we'll keep adding complexity, as you will see. So basically, more realistic storage elements have a control mechanism for setting Q. So we will see the RS latch soon, but I want to give you a bigger picture first before we go into RS latch. Because we're going to go into memories a lot later on. RS latches, what we're going to discuss in this lecture are expensive memories. They're going to be big, expensive in terms of area, power, latency, everything. Most of memories that we have are not expensive memories. They're very small, very cheap, like SRAM, for example. SRAM is actually one of the more expensive ones. So this is an SRAM. Just to show you that what we have seen earlier is actually used. This cross-coupled inverter actually is used in caches, for example, of your processor. That's the cross-coupled inverter that we have seen. It has a control mechanism, as you can see, which I'm not going to go into right now. But basically, by enabling and disabling these transistors, you can put a value in or out into that Q and Q bar. Okay? Don't worry about it. If you don't understand how this works right now, you can actually imagine how this works. This is the transistor that you enable or disable. Okay. We will get back to SRAM and actually DRAM later at lecture 20 or so. Okay. But today we're going to cover latches and flip-flops, expensive stuff, because these expensive stuff is also needed when you actually have design processors. To give you the big picture before we go into the suspense or finish the suspense of how you actually control this inverter expensively, these are very fast parallel access, but very expensive. 1 bit will cost tens of transistors. Static RAM caches in processors, relatively fast, not as fast as latches and flip-flops. It's also expensive, but less expensive. 1 bit costs about 6 transistors. Dynamic RAM, which is essentially all of the memories of today, they're slower. It has a lot of issues, like special processing, but it's very cheap. 1 bit costs only 1 transistor plus 1 capacitor. That's why you can have gigabytes and gigabytes of it. Other storage technologies, even cheaper, flash memory, hard disk, tape, they're much slower. Access take a long time. They also have some other characteristics that we will talk about, even cheaper. Okay? We're going to build a memory hierarchy based on this. So we're starting with the very basics of the memory hierarchy with latches and flip-flops. But those cross-coupled inverters are actually the beginning of everything. They're actually used in SRAM. Okay. Now we're going to build a controllable cross-coupled, controllable something that builds on the concept of cross-coupling. It's going to be called the RS latch. Initially, when you may see it, it may actually be surprising. But you need to work out the equations and make sure you understand it. It looks like this. Your book has a NOR version of it. I'm going to show you a NAND version of it. But if you cross-couple 2 NAND gates, it's called an RS latch, reset or set latch. Okay? So this is one NAND gate over here. Its output is Q. This is another NAND gate. Its output is Q bar. And Q is connected to one input of this bottom NAND gate. R is connected to the other input. And Q bar is connected to one of the input over here to the top NAND gate. And S, set signal, is connected to the top. Now, Data is stored at Q in versus Q bar, just like the previous one, but now we have a mechanism for setting or resetting. We added more inputs and more complex gates, as you can see. S and R are control inputs, so that we can set or reset Q. Now there's a quiescent or idle state where both S and R are held at 1. If both S and R are 1, whatever was stored in Q remains, and whatever was stored in Q bar remains. So basically, if S and R are 1, whatever value was there is remembered, right? So we're going to call it Q previous. Q equals Q previous. You can convince yourself this is the case, and your book actually helps you a little bit also. Now, if you want to set this, what do? We drive, okay, this is a mind of its own. We drive S to 0 while keeping R at 1. Now, if you drive S to 0, this AND gate evaluates to, well, this NAND gate evaluates to 1 because this AND is 0 and there's a inverter. Q becomes 1, and this is 1, R is 1. We said that, keeping R at 1. And this becomes 0. So this is 0. So we don't violate anything. That sounds good. So basically, if you want to set, you drive S to 0, and Q becomes 1, while keeping R at 1. Okay? If you want to reset, you do the opposite. You drive R to 0, while keeping S at 1. And again, let me go through it again. I think it's the same thing happens at the bottom, basically. The things flip. If R is 0, Q bar becomes 1. And this is 1. S is kept at 1, so Q becomes 0. So our invariant is satisfied. Everything is good. This is good. Now, the surprising part is you don't want to do this. Your book is not as clear about this, but you don't want to do this in the end, because this leads you to a metastable state later on. There are two reasons why you don't want to do this. S and R should never be 0 at the same time. Because if you do S and R 0, Q is 1, Q bar is 1. You violated something fundamental, right? This should immediately raise flags in your head. My basic logical assumption is Q and Q bar are complements of each other. If I set S and R to 0, I get Q equals Q bar. I violated the rules of Boolean algebra. So I should not do this. And that gut feeling is correct. You should not do this. Even though you may think that it's okay, it leads to some metastable state. So we're going to call it forbidden, basically. So this is our truth table. If R and S are 1, Q keeps the previous value. If you want to set Q to 1, you input S 0, R 1. If you want to reset Q to 0, you do this, 0, 1, and you never do this. Let me finish, and then we're going to take a break. Why not? Well, this should be enough. But there's another reason. Essentially, this is what I said. You break your invariant, which is logically wrong. The second reason is, if S and R, they were 0, and if you transition back to 1 at the same time, basically figure out what's over here, Q and Q bar begin to oscillate between 1 and 0. And their final values depend on each other. This is metastability that we're going to see. And you can actually try to simulate this on your own, but there's some analog simulation that you may need to do. In the end, because you violated something, depending on the strength of the structures, the oscillation may actually eventually settle to Q being equal to 0 or 1. But there's some randomness in this. This could be a random number generator, actually. But let's leave it at that for now. Random number generators actually take advantage of some sort of lower level hardware unpredictableness. And this could be one of those. Okay, we're going to talk about that. Essentially, we don't want to do that. So how do we fix the problem? Let me introduce the gated D latch, and we're going to take a break. So how do you guarantee correct operation of this? Well, ensure no one is able to set S and R to 0. I introduced 2 more NAND gates. Sorry. It's becoming expensive. Basically, now what I've done is D is the input that I want to set Q with. And I have a write enable signal. If this write enable signal is 0, I don't change anything over here. If that write enable signal is 1, Q should get the output of, Q should become equal to D. Basically, Q takes the value of D when right enable signal is set to 1. Let's go through this. If this is 1, you get D over here, inverted and inverted again, right? If this is 1, you get D bar over here, and again, inverted again. Okay, again, you need to go through the truth table, which I will show you in a little bit. But SNR now can never be 0 at the same time. Again, you can convince yourself because it's really controlled by right enable and D. Make sense? So you could have said earlier, SNR, I'm going to forbid it so that no one does it. Whenever you do that, when you connect complex circuits to each other, at some point SNR may become 0. Okay? You can say, I forbid it and everybody obeys that rule. No. It is possible that everybody potentially obeys that rule, but someone used that circuit and there may be a glitch, as we will see later on in the timing lecture, where SNR may become 0 at the same time and you run into a metastable state that you may not be able to get out of for a long time. Okay, so let's take a look at this gated D latch operation. This is input, there are two inputs, right enable, D. If D is 0, if right enable is 0, nothing changes. This SNR actually are 1, if you remember. And if SNR is 1, Q is equal to Q previous. If right enable is 1 and D is 0, then Q becomes 0. If right enable is 1 and D is 1, Q becomes 1. So basically, this is what we want. We rewrite D into Q if right enable is 1. Otherwise, Q remains unchanged. And this is a good structure. This is basically, this doesn't violate any logical principles depending on inputs. And it also doesn't have metastable states. Okay, this is the point. We will take a break and then we'll build up to other structures. So let's be back when the bell rings.
Questions.
Yeah. All right. Okay. So now we know how to build something that doesn't violate any logical principle and also doesn't have a metastable state, which you will learn about in the timing lecture. But you see that we had to use 1, 2, 3, 4 NAND gates for it. And you remember from the past, a NAND gate is some number of transistors, 4 transistors, right? So that's 16 transistors for you. Not cheap. Just to give you an idea, a DRAM cell, 1 bit, it stores 1 bit in 1 transistor, using 1 transistor and 1 capacitor, much smaller. Okay, so hopefully this is all clear right now, because we're going to build up from now on. We're going to make it even more complicated for our purposes later on. We're going to add a copy of it in front of this one. But there will be a good reason for it, as you will see. So we're going to actually double the number of transistors that we're going to use in a sequential circuit, in a finite state machine specifically, soon. Okay, but please, some of you asked, what should we do readings in the book? If you understand everything in the lecture, I don't think you need to do the readings, frankly. But of course, readings are good for understanding better in the lecture. But your book also has parts that are not covered in lecture. And I would recommend focusing on parts that are covered in lecture. Okay, and you can recognize them. Okay? For example, we didn't cover multiplier. You don't need to do the readings on multiplier unless you feel like you want to learn about multipliers. Okay? I'm not going to ask you about multipliers. And if I ask you about multipliers, I'll tell you what a multiplier is and then build stuff. Okay? You may need the multiplier later on, though. Okay. Okay, so this is the gated D latch. Now we store 1 bit. How do you store more bits? I'm going to introduce the concept of a register, which is a very simple concept. You basically put these multiple D latches in parallel. So how can we use D latches to store more data instead of 1 bit? This is our D latch representation. As you can see, it has a right enable signal and D. I just rotated it this way, as you can see, and I got rid of the Q bar. We don't need Q bar for this purpose. Basically, use more D latches and put them in parallel like this. If you want to store 4 bits, for example, these are 4 bits. This is the most significant bit in general. That's the notation. This is the least significant bit, but we're going to see that later on also. Basically, we have a single write enable signal for all latches to enable simultaneous writing to of a 4-bit value. This is a 4-bit value, right? And this is the 4-bit output. Now we can basically, this is a structure that stores more than 1 bit and can be read from and written to. It's a register. That's the definition of a register. This register holds 4 bits and its data is referenced as Q bracket 3 colon 0 close bracket. Okay, we're going to use this notation and you're going to use this sort of notation in Verilog later on. So it's simple. But this is a module also. So this is the internal representation of the register module. This is the module level representation of a register. If you see something like this, this is register X, a 4 input, 4 output register with a write enable signal, as you can see. Okay? Later, we're going to add a clock to it for a good reason, as we will see. Okay, now let's build memories a little bit. Because this is a register that's a standalone register, right? What if you had many of these registers? Like 4 of them, or even 2 of them? and you want to choose between register 0 and register 1. You can put those registers, let's say, on top of each other, and then pick one of them, multiplex the data outputs. But you need to decode the address, figure out which one you're addressing, and then pick the value coming from the right register. Okay, we're going to build that memory right now. I kind of explained it. But before we build that memory, what is memory? Memory is really comprised of locations that can be written to or read from. An example memory array with 4 locations may look like this. Logically, this is, you can see basically 4 locations require 2 bits of address, 0001, 1011. Every unique location in memory is indexed or addressed with a unique address. 4 locations require 2 address bits because you need to have log 2 to the number of locations, right? In this case, I show you what data is stored. Each location stores 8 bits. Again, this is an example. I'm going to show you another example at the logic level soon. This is all higher level. Addressability is the number of bits of information stored in each location. So if you look at this example, location 00 stores 8 bits. So you could have a register that's 8 wide, right? So this register, instead of having it 4 wide, you could have 7 to 0 and Q7 to 0 over here. Makes sense, right? So you can basically change the concept to different, parameterize the concept. Okay, that's addressability. And the entire set of unique locations in memory is referred to as the address space. Okay, in this case, our address space is 4. We have 4 locations in memory, right? Does that make sense? And each location has 8 bits. Okay. Okay, a real memory is much larger, billions of locations. And each location may have more than 8 bits, right? Okay, we're going to see those memories again later on. Now we're going to build a very simple memory, but the basic concept is applied to later memories also. So how do we address memory? So let's now implement a simple memory array with 3-bit addressability, meaning each location has 3 bits, an address space size of 2, meaning only 2 locations, location 0 and location 1, each location storing 3 bits. Now you can imagine what we're going to do. We're going to have one register that's 3 bits as opposed to 4 that we've shown earlier. That's going to be in our location 0. And we're going to have another register, another 3 bits in location 1. That's our total 6 bits. Nice. Now we're going to figure out which one to access based on address decoding. We're going to add a decoder. And that decoder will also enable us to select or multiplex out the right output from the right register. So we're going to start with this. This is our 1 bit. And we're going to basically replicate this everywhere, but we're going to do it just like a register earlier. Okay, how can we select an address to read? This is what I said in Word, let's say, written form. Because there are 2 addresses, address size is 1 bit. That's what I kind of said, right? Now, these are our bits. Or you can think of this as our register also, but I want to show the internals also, because internals are quite regular, as you will see. I'm going to add some circuitry. So this is location 0, these 3 bits, and these 3 bits are location 1. So I need to have a way of, whenever I say address 0, I need to get the value here, 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 out. So how do I do that? I need a decoder, basically. So I take the address bit. There's only 1 bit. If address bit is 0, I get the data out. So this is a multiplexer. So this is a decoder. It's a 2-to-1 decoder. And this is a multiplexer. A multiplexer always has a decoder inside, remember. So decoder is actually, multiplexer is actually kind of distributed. But let's examine this. If address bit is 0, this wire evaluates to 1, meaning that the input to these AND gates are all 1, meaning that the result of this AND gates is whatever is stored in this flip-flop, or sorry, latch, in this case. You'll see the flip-flop later. So it drives here. And because of the function of the decoder, if address bit is 0, this is 1. If address bit is 0, this wire is 0. And this AND gate evaluates to 0. So the output of this OR gate is not dependent on any of these, because this address is not decoded. And the output of this, each of these OR gates is, which muxes, is actually dependent on the values that are stored up here. Make sense? Again, there's no magic. This is all basics, what we have seen. Now, we'll call this the word line or decoded address. This is the address decoder. And this is multiplexer together with decoder a little bit. Okay? So we've seen these structures before. And you can convince yourself that this operates this way. I've kind of gone through it, but if you haven't followed completely, you can do it. It's all logical. We built up all of these structures. There's no magic here. You can actually go through the transistor level of every single one of them. Okay. So remember, multiplexer, just to jog your memory, it selects one of the n inputs to connect it to the output. Here, we're selecting between one of the two inputs. There are two locations, 1, 2. We're selecting between either of those based on the address, 0 or 1. Okay? And we're doing it in parallel for these two, and these two. And if we're reading from address 0, we're going to get the values of these in D2, D1, D0. Okay? Okay. So that's reading. Reading is good. Now let's write to this. Writing is going to be similar to what we have seen earlier. We're going to have a write enabled. How can we select an address and write to it? Same things over here. Now we're going to, in addition to the address, we're going to also have a write enable bit. Address is going to do the same thing. Ignore the write enable bit. You get to the previous picture that I showed you. Write enable, if write enable is 1 and the address is 1, this gate will evaluate to this one, and then write enable of this one will be 1. Okay? If write enable is 1 and address is 0, then you write to the top part. Okay? If write enable is 0, then you're not writing. Okay? So the operation is basically what we have seen earlier, except you're controlling multiple locations gated by the signals coming out of the address decoder. Remember, this is still our decoder. So if you want to write to address 0, you set the write enable signal to 1 and set the address to 0. Make sense? Okay, good. Now let's put it all together. Let's enable reading from and writing to memory array. This is what it looks like. Actually, I've shown you this already. But you need to have a data input. I kind of shown you the data input also, actually. This is the data input that you write with the write enable signal. And this is essentially our gated D latch earlier. So it operates exactly as what we said. If you're writing to address 0, then this input D gets transferred into the output of the D latch, which is whatever is over here, Q essentially, but it's not shown over here. But if you want to write and read together, you need to have the write circuitry, which is what I've shown you, and you need to have the read circuitry, which is what I've shown you earlier. And this is our final memory. This is a perfectly functional memory with 2 locations, where each location stores 3 bits, and you can read from it, and you can write to it. The granularity of reading is 3 bits at a time, and you can do it at only 1 location at a time, right? You can do it at address 0 or address 1, but you write to all 3 bits at the same time, or you read from all 3 bits at the same time. Make sense? Okay, now you want to make it bigger? Here's a bigger one. Not that much bigger, but we multiplied it by 2. Now we have 4 locations with 3 bits. If you want to make it 4 locations, 8 bits, add 5 more of these to this side. I don't think we have enough space over here right now. But let's take a look at it. What I have done, made the address decoder bigger. If you have 4 locations, your addresses should be 2 bits, and your decoder should decode 2 bits. Remember, decoder is a pattern detector. It detects which pattern is enabled. The pattern, it could be 00011, and that's essentially what we're doing. That's why we cover decoder as one of the basic circuits. It enables us to really address each of these 4 3-bit locations. And multiplexer here enables us to select each of these bits, D2, D1, D0, from one of the 4 locations. Okay? Yes?
Quick question for better understanding.
Yeah.
Are we kind of reading one location all the time, right?
In this case, yes.
Okay.
Basically, yes. As long as you're applying some input, you're reading one location all the time, yes. But you can think about how to disable that using tri-state buffers, etc. Right? But yeah, you can build other structures on top of this. Okay, so this is our memory array. Hopefully, everybody understands it. Now, this is an example from one of the books on reading location 3. You can read location 3, supply address 311, set write enable to 0. These are the gates and wires that are enabled. As you can see, the data that's stored in location 3 latches gets propagated to output of the memory. So essentially, the inputs to the memory are these, are address bits, write enable bit, and also the data bits that you want to write if the write enable bit is 1. And the outputs are really these bits. Okay? And you can simulate this and you can convince yourself, hopefully. Okay, so decoder, I'll go back. Remember, when I introduced the decoder, I said it's useful in determining how to interpret a bit pattern. It could be the address of a location in memory that the processor intends to read from. That's exactly what we did. So we use the decoder to figure out which of these 3 bits to read from, 3-bit structures to read from. And this is recall the multiplexer. This is just to show you that there's no magic in any of this. Okay. Okay, now I'll have a little bit more fun because you're going to do this in your FPGA labs. You can implement these logic functions using memory as well. Basically, you can store values in your memory and you can implement functions. We have seen this actually before in decoder, but it's going to be similar. You can have memory arrays that can perform Boolean logic functions. So in this case, our truth table looks like this. As you can see, this is an AND function. You can have 2 to the n location, n-bit memory. It can perform any n input, m output function. You have seen this before, actually, in the last lecture, but now we can have actually sequential storage that enables this. And your book actually kind of obfuscates things, but meaning it doesn't show everything over here. It basically says that there's a bit line, but you can imagine some things that are connected over here. So I will not go through this in detail, but you can think about it. So lookup table, this is a lookup table. It's a memory array used to perform logic functions. Each address is essentially a row in the truth table. Each data bit that's stored corresponding to that row is the corresponding output value. So this is basically, you can build this truth table with what I've shown you over here. I think my picture is better than your books, frankly, because just ignore these 2 parts over here. Essentially, you have you can implement the truth table by storing the right bits initially over here, meaning this is your truth table, right? If the address is 0, 0, your output should be 0. Only if the address is 1, 1, your output should be 1. So you store 0 here, 0 here, 0 here, 1 here. And whenever you apply an address combination, you will get the AND function. Makes sense, right? Okay. So if you're confused about the bitline terminology, don't worry. This is a more generalized terminology over here that we're going to go into later in lecture 20 or so. Okay. So why am I telling you this? Because this is the type of structure that's used in a lot of FPGAs to implement logic functions. Your book also talks about that. I will not go through this. If you're interested, you can look at it. But I'm not going to have you responsible for this because it's not also that fundamental. But essentially, FPGAs enable things that look like this. You can have different lookup tables. And by programming the inputs, the data values stored in the lookup tables, you can implement different functions in FPGA. So when you actually put your logic that you design onto the FPGA, you will program some of these lookup tables. This is another programmable logic, essentially. You program the bits inside the lookup tables. You can think of it as you program the bits over here such that you implement a logic function. Right? That's quite powerful, but expensive also. And A and B, remember, an A and B, if you want to implement it using purely combinational logic, it's 1 gate. It's an AND gate. If you want to implement it using a lookup table, you need all of the circuitry, right? That's why FPGAs are expensive in terms of hardware. To do the same function as a hardwired circuitry, they need to use a lot of gates. But the advantage is they're quite programmable. Okay. Okay. Well, this is what we covered also last time. Previously, we had hardwired. Remember, we basically, in the last lecture, we implement the function that outputs 1 when there are at least 2 1s in a 3-bit input. And I had hardwired the inputs to logic 1 and logic 0. But you can actually have memory locations associated with them, and you can do the decoding. Okay. Any questions? Now let's jump into sequential logic circuits. We have some basics on how to store data. What is a sequential logic circuit? We've examined this. Now we'll remember how to use what we have built to remember past inputs. But I will introduce some concepts first. How many of you have used something like this? Okay, good. This is a combinational circuit. It's a combinational lock. When the combination is correct, the thing opens. And the combination, basically the output meaning that thing being open or closed, locked or unlocked, depends only on the current inputs. How many of you have used this where it remembered what you've done? Probably not this. Probably you use something like this. How many of you have used this? This is a little bit more secure, potentially. I don't know, maybe. But this is sequential. Basically, this opens depending on past inputs, right? Let's take a look at how that operates. This is a notion of state. Basically, this has a notion of state. The other thing doesn't have a notion of state. So in order for this lock to work, it has to keep track of past events, meaning it has to remember things. So for example, you can set the passcode to turn right to number 13, and then turn left to number 22, and then turn right to number 3. And if you do that sequence correctly, this thing unlocks, assuming you start with the locked state. Okay? So there's always an assumption. What is the state that you start with also? Okay, basically, the lock is not open, and no relevant operations have been performed. That's state A. And then you may have another state that's locked, but the user has completed R13. That's state B. And then you can be locked, but the user has completed R13 and left 22 in sequence. That's state C. And then state D is unlocked, where the user has completed R13, L22, and R3 in sequence. So there are 4 states, basically. The state of a system is a snapshot of all relevant elements of the system at the moment of the snapshot. That's state, basically. Make sense? To open the lock, you need to go through states A through D in order. If you mess up at some point, you go back to state A. This is actually a finite state machine. I'm going to introduce that more formally later on. Basically, if anything else happens, for example, if you, instead of going to L22, you go to L21 or L5. After R13, the lock returns to state A. There's an internal finite state machine there. And this is our finite state machine, basically. So this is a state diagram. This completely describes the operation of the sequential lock. And you can convince yourself. This is from your book, one of your books. You can read the book also. It says essentially the same thing that I said over here at this point. So let's take a look at an example over here. This is state A. We're locked, and no operation has been done by the user. If the user inputs anything other than R13, meaning moves the knob to somewhere other than right 13, you stay here, right? But if they do R13, then you go to a state still locked, but now you're waiting for L22. And if the user actually inputs L22, you go to another state that's still locked, but you're now waiting for R3. And if the user inputs R3, does R3 at that point, right, turns the knob to location 3 to the right, then you unlock, okay? And there needs to be some action to make it locked again at some point, but we're not going to talk about that. Okay, so we will understand these state diagrams fully later today, but hopefully this is something you can empathize with based on what I said, right? This fully describes the operation of the state. We're going to use these state diagrams to fully describe the operation of a sequential circuit, essentially, because that is a sequential circuit implemented using non-electronics. I mean, it could be electronics internally, actually. Okay, so let me introduce something else very quickly. Sequential lock we saw is an asynchronous machine, actually. Modern computers are synchronous machines, so we're going to make our life easier so that we don't go crazy over here. We're going to use synchronous circuits. And if you ever design an asynchronous circuit, you will understand what I mean by going crazy. Okay, so basically, in an asynchronous circuit or machine, state transitions occur when they occur. There's nothing that synchronizes when each state transition must occur. This is very hard to design in general. It's prone to a lot of bugs, etc. Whereas if you're synchronous, there's something that dictates when state transitions take place. Basically, you divide time into intervals, and state transitions take place after fixed units of time, and we're going to call it a clock. Controlled in part by a clock, but in part by other things also, as we will see soon. So these are actually two different design paradigms of machines in general, and also computers in particular, with different trade-offs. Okay, let's take a look at another simple example of state. How many of you drive cars? Okay, how many of you have seen a traffic light? Okay, more than, probably that's a superset of people who drive cars, right? Hopefully. Well, I don't know actually. Yeah, hopefully. Okay, but basically, a standard Swiss traffic light has 4 states. I say Swiss traffic light because this is not the same everywhere in the world. There are different conventions. You may have figured out in the wrong way or in a bad way potentially. Because this is a safety critical system. So, yeah. So basically you're green, you could be yellow, you could be red, you could be red and yellow. Hopefully I got this right. Okay, and they have different meanings, which we're not going to get into. If you drive cars, you know the meanings, hopefully. And the sequence of these states are always as follows. You go from A, B, C, D, and then back to A. Now, there may be different amounts of time you spend in each of these states, but they're controlled by something synchronous. It's actually a clock. So you could actually design a Swiss traffic light. But how do you change state? So I'm going to introduce the notion of clock, and this is going to be important. This may be surprising initially when you see it, but when you understand it, it's really what enables us to synchronize. So when should the light change from one state to another? That's the key question over here. So basically, we're going to use a clock to dictate when to change state. This is essentially something that oscillates. It's a signal. You can think of it as a wire that goes high for some time, and that goes low for some time, and then goes high for some time, and that goes low for some time, between 0 to 1, logically. And it keeps doing that forever. Okay? People actually design these things, using quartz crystals, for example. But this could be a driver of when state changes. For example, this is what it looks like. For one clock cycle, you may stay at state A. When the clock cycle finishes, at the beginning of the next clock cycle, you may go to state B. You may stay in state B for another one clock cycle, and when the next clock cycle begins, you go to state C. And you could keep doing that. That's a very, very simple one. Or you could design a state machine that stays in each state different number of clock cycles. That's also possible. In fact, it should be possible based on what we've seen so far. You should be, well, not you should be able to, but you could design a circuit that stays in different clock cycles for different states, different amounts of time. We're going to design something different later on. Okay, so at the start of the clock cycle, the system state changes, meaning this clock edge, positive edge clock. During a clock cycle, the state stays constant. Keep it that way because you do some computation potentially during that time. In this case, the computation is very simple. You stay at that state, you keep things green. But we're going to see a smart traffic light. During that clock cycle, it may actually do some computation and say, I'm going to stay in green for a little bit longer, right? You may have seen those smart traffic lights. Sometimes you don't think they're smart, of course. It may basically compute something. How much traffic is coming from here? How much traffic is coming from here? How much backup has happened over here? During that clock cycle, you do that computation and you decide, I'm going to switch the state to B. Make sense? Or you decide, I'm going to stay in A. So at the beginning of a clock cycle, you go to a new state potentially. During the clock cycle, you do some computation. At the beginning of the next clock cycle, based on the computation you've done in this clock cycle, you go to another state, or you stay in the same state. Make sense? This is a state machine, basically. Okay, in this traffic light example, I kind of assume that with traffic light stays in each state an equal amount of time, but hopefully I motivated why you may want to do some other computation. Okay, so essentially clock is a general mechanism that triggers transition from one state to another in a synchronous sequential circuit. It synchronizes state change across many sequential circuit elements. There may be many, many elements like this, many, many traffic lights in this particular case. You have combinational logic that evaluates for the length of the clock cycle. So that smart traffic light is it's taking inputs from many places. It's doing some computation. That's combinational logic. It's producing some output saying, do I want to go into, what is the next state that I go into, and what do I output? What should the color of the light be? So it's basically doing some combinational computation. At the end, it's changing the state, and it's also potentially providing an output, right? So that's combinational logic. Sequential logic is storing the state, whether the state is green, red, etc. Okay, so clock cycles should be chosen to accommodate maximum combinational circuit delay, meaning you do have some computation. You imagine some smart traffic light that has some computation. You design the circuit, and you choose your clock cycle based on whether you can actually satisfy that computation. Make sense? So we're going to see timing later on. We're not going to discuss it today, but keep this in mind. Okay, so this is synchronous. Clock enables synchronous. Synchronous control can be easier to get correct when the system consists of many components and many states. Asynchronous is very hard. If you want to design a smart light using asynchronous, no clock, no notion of clock, that's actually very difficult. You'll get into a lot of race conditions, and you may actually get a race condition, meaning some state changes, another state changes, and you cannot control things easily. Okay, asynchronous control may be more efficient because there's no clock overhead. Here, we're going to see later in timing, for example, there's an overhead of clock because you need to, this clock needs to go into everywhere in the machine. Every state element should be connected to this clock. That's an overhead, first of all. You need to generate that clock. That's another overhead. And you need to satisfy the timing with respect to clock. That's another overhead. And we're going to see those issues later on. So synchronous has a lot of overhead in terms of latency, but it's a whole lot easier to design and people don't go crazy designing it, okay? But asynchronous is very interesting for research purposes. Okay, so we will assume synchronous systems in most of this course. Now that we know all of these concepts, let's design a finite state machine, or let's introduce finite state machines first. So what is a finite state machine? It's essentially formally a discrete time model of a stateful system. It has state, as we have seen. Each state represents a snapshot of the system at a given time, as I already said. And usually FSMs are depicted pictorially. They don't have to be, but pictorially it shows the set of all possible states that a system can be in and how the system transitions from one state to another. An FSM can model many things, essentially any machine. It can model the world, actually. We have a very big and complicated FSM, finite state machine, except we don't know how to represent it, I think. Okay? We will see later. We're not going to model the world in this course. We're going to model a microprocessor. We're going to design, I'm going to show you a finite state machine of a very simple microprocessor in lecture 11, 12 or so. Okay, we're going to build up to that. Okay, basically an FSM enables us to pictorially think of a stateful system using simple diagrams. I've kind of shown you a diagram. Now we're going to see more diagrams. So it consists of 5 elements. I'll go through this quickly. A finite number of states. That's why it's called finite. Infinite is something that we cannot think about and design. State is essentially the snapshot of all relevant elements, as we've discussed. A finite number of external inputs. A finite number of external outputs, as we will see. An explicit specification of all state transitions. How to get from one state to another. And an explicit specification of what determines each external output value. Essentially, how you generate the output. Okay? So it's really a combination of sequential and combinational logic. So there are 3 separate parts in logic. One is the next state logic. How do you go from the current state stored in your state register, which is the next element, to the next state? What is the value of your next value of your state register in the next clock cycle? State register stores the current state of the system. And output logic determines what should the output be based on the inputs and the current state register. Okay, it looks kind of like this, basically. This is our state register. We're going to add a clock to it soon. So far, we haven't added, remember, the D-latch. D-latch is not going to work for this purpose, so we're going to introduce something else. This is our state. Based on the state, we can generate some output. That's a particular type of machine. Don't worry about that. But based on the inputs and the current states, we determine the next state. Actually, output can be determined based on the state as well as the inputs as well. This doesn't depict the general case. Okay, this is state register, as I said. At the beginning of the clock cycle, next state is latched into the state register. Remember, synchronous. Next state is latched at the beginning of the clock cycle immediately. There's some timing we're going to ignore for now. And we want the next state to be, that state to be available during the entire clock cycle so that we can do computation on it. So we want an element that satisfies these requirements. So we have sequential circuits, state register. Input is the next state, output is the current state. And at the edge of the clock cycle, current state gets the value of next state that is generated over here. It stores the current state and loads the next state at the clock edge. Combinational circuits, essentially the next state logic determines what the next state will be, and the output logic determines the outputs. Okay, now let's take a look at the sequential circuit. How do we implement the state register? Basically, we want two properties. We need to store data at the beginning of every clock cycle. Clock transition determines when input is acquired. Even if we're staying at the same state, we want to obey this, right? Because that's what synchronous means. Hopefully everything was clear so far. And the data must be available during the entire clock cycle. Hopefully I motivated that earlier because we have a lot of inputs and we want to do our computation and we want to have the entire clock cycle, and we set the entire clock cycle so that we can make an intelligent decision when the clock rises again, goes from 0 to 1 again, right? So let's take a look at this pictorially. This is our input, register input, and there's our register output. If our input changes, this is basically next state. So when I say register input, this is the next state over here. This is the output, current state. And when the clock rises, at the positive clock edge, in other words, register input that you have gets latched into the register. So this is what we want. Here, the combinational logic operates using value 0 inside the register input. And that value doesn't change until the clock rises again from 0 to 1. The register captures the value only at the clock edge from 0 to 1. Okay? This is very important because we want that value not to change because the combinational logic is evaluating based on the past input. If that value changes in the middle over here, that combinational logic will get confused because that's one of the inputs, right? Okay? Okay. So this is the desired behavior we want. Basically here, there's some change in the input, but that doesn't get reflected because it doesn't happen over here, right? Here, there's some change in the input, it gets reflected at the clock edge again, right? Basically, if input changes in the middle, but not when the clock rises, at the synchronization point, then you don't want the output to change, okay? So this is what we want. Now, the problem with latches, what we designed so far, it doesn't give you what we want. So this is our gated D latch. Currently, we cannot simply wire a clock to the right enable of a latch. Whenever the clock is high, the latch propagates D to Q. Basically, the latch is transparent. I'm going to show you in a little bit. Basically, assuming that you wire the clock to the right enable, this is one way you could actually build what we want. It's not going to work, as we will see, because latch immediately changes its output value. And you can imagine this based on what we've seen so far. So this is our register input. This is where D changes. So this is D. And we set clock to right enable. Over here, the behavior is fine, right? Because right enable, meaning clock is 0 over here. When clock is 0, the input changes, Q doesn't change. Okay? That's the D latch we've seen. Unfortunately, here, clock is 1, and the input changes, so the output immediately changes. This is not what we want, because we want the state register to change its output only at the positive clock edge, when the clock becomes goes to 1. Again, another undesired behavior happens over here. The clock is high, meaning right enable is 1 over here. If D changes, the input changes, the output immediately changes. Again, that's not what we want. We want the output to change only at the clock edge, only over here, 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 and not anywhere in the middle. So these are problematic, basically. This is why we cannot use a latch as a state register in a finite state machine, because it will change, at least the way you wire the clock over here, it will change, and there's no way of wiring the clock to a D latch. It will change its output in the middle of a clock cycle, and that's not what we want. We want the state to be stable for the entire clock cycle. So how do we fix this? Basically, how can we change the latch so that D input is observable at Q output only at the beginning of next clock cycle, and Q is available for the full clock cycle? Basically, we want a new storage element that allows us to read the current state throughout the entire clock cycle, without changing, without the current state changing, and not write the next state values into the storage elements until the beginning of the next clock cycle. So now I'm going to introduce D flip-flop. I'm going to double the size. We want state change on clock edge and data available for a full clock cycle. We have a D latch. I'm going to call this the first latch, and this is the second latch. And you've seen both of them before because they're the same thing, except we connected them like this. And input is here, and output is here. There's some intermediate thing that is not going to be visible to anyone. So what happens? I'm going to wire the clock this way. Clock high enables, right enables this one. Clock low, right enables this one. Okay. Now let's take a look at its behavior. When the clock is low, this is right enabled. D value gets passed over here based on the operation of the D latch, right? But it doesn't go over here because clock is low and right enable is 0 over here. Now when the, essentially we call it first latch propagates D to the input of the second latch. Q doesn't change, which is exactly what we want. Now only when the clock is high, second latch latches D, meaning when the clock, Q stores D, right? When the clock goes high, this is right enabled. And then this D that you passed over here when the clock was low goes over here. Right? So in other words, at the rising edge of the clock going from 0 to 1, Q gets the value of D. Make sense? Okay, I'm going to take the question later because we're very close to the end soon, but hold it for a moment. So you represent it like this. Hopefully that's clear. You represent it like this. This is our abstraction module level. You have a D latch, Q bar. You don't need the Q bar necessarily. And essentially at the rising edge of the clock, Q gets assigned D. At all other times, Q is unchanged. Internally, it's 2 D latches, but now it satisfies our state register behavior. Okay, does this, yeah, quickly.
Question was, when we have the clock enabled, can we then write? Because I think we can't, I might be mistaken.
When you have the clock enabled, you can write over here, yes?
No. On the other side, we write on first D latch, don't we?
No, you don't, because this is inverted. So when the clock is low, this D gets propagated over here. Makes sense? Only when clock transitions from low to high, the value over here gets propagated over here.
When it's high, we can't load anything into the first D latch.
That's right, yes, exactly.
But we were able to do that in the infographic before.
Okay. Okay, that's a very good question. We'll talk about that later. Yeah. Okay. So this is also called a rising edge triggered, clock edge triggered flip-flop. The flip-flop samples D on the rising edge of the clock. This is called the positive edge. When clock rises from 0 to 1, D passes through Q. And when otherwise, Q holds its previous value. Okay. I think this is actually explaining everything that I said earlier. This flip-flop is an edge-triggered state element because it captures data on the clock edge, as opposed to level-triggered state element, which is a latch. Okay, if you want to actually do this for multiple bits, you can have multiple parallel D flip-flops. This is a 4-bit state register, and you can represent it this way, as you can see. This register stores 4 bits, and this is 4 wires. And internally, remember, this is what it looks like over here. Okay, I think this is a good place to stop. Because now, given all of this, we're going to build a full finite state machine starting tomorrow. And then we're going to keep building up. Okay, I'll see you tomorrow.